On November 5th, 2018, at a distance of roughly 11 billion miles from the Florida launch pad it left in 1977, Voyager 2 crossed into interstellar space and ran straight into a wall that should not exist. No spacecraft had ever measured this boundary directly and lived to send the numbers home. No model built before that day predicted what the instruments actually recorded. It is not a clean edge between the solar system and the galaxy. It is a blazing, invisible barrier of plasma, tens of thousands of degrees hot, and nobody built the physics to fully explain why it's there. Stay with me, because what NASA confirmed about this boundary is still not fully settled science. If you're new here, this channel covers the outer edges of what we actually know about space, mission by mission, fact by fact. So if that sounds like your thing, subscribe now, it's free. Let us go back to the beginning. Voyager 2 launched on August 20th, 1977 from Cape Canaveral, 16 days before its twin Voyager 1 lifted off from the same coastline. Both spacecraft were built for essentially one job: fly past the outer planets during a rare alignment that happens roughly once every 176 years, take pictures, gather data, and wrap things up within about 4 years. NASA had originally hoped to send a fleet of probes to visit every outer planet in a single sweeping grand tour, but budget realities in the early 1970s trimmed that dream down to 2 spacecraft with a far more modest mandate. Nobody involved in building either probe expected them to still be transmitting data from beyond the solar system nearly 50 years later. The electronics were rated for a fraction of that lifespan. The plutonium in their power sources was chosen because it decays slowly enough to outlast the mission, not because anyone planned for a half-century of continuous operation. Voyager 2 ended up doing something no other spacecraft in history has done before or since. It flew past Jupiter, Saturn, Uranus, and Neptune, all 4 giant planets, on a single trajectory, using each planet's gravity to sling itself toward the next. Along the way, it delivered the first, and to this day, only close-up images of Uranus and Neptune ever taken by any spacecraft, along with the discovery of new moons, previously unseen rings, and a bizarre tilted magnetic field around Uranus that scientists are still working to fully explain. That grand tour wrapped up in 1989. Everything that has happened since has been bonus time nobody explicitly planned for. To understand why what happened at the edge of the solar system mattered so much, you need the basic picture scientists were working from. The sun doesn't just sit there radiating light, it constantly exhales a stream of charged particles called the solar wind, and that outward pressure inflates a vast magnetic bubble around the entire solar system called the heliosphere. Picture it as a ship sailing through the galaxy, pushing a bow wave of solar plasma ahead of it. Eventually, far past the orbit of Pluto, that outward pressure runs out of strength and meets the resistance of the interstellar medium, the thin plasma and magnetic field that fills the space between stars, left over from nearby supernovae that exploded millions of years ago. The boundary where those 2 pressures balance out is called the heliopause. Scientists had good reason to expect the boundary to behave in specific, predictable ways. The plasma should get colder and denser once you cross it. Cosmic ray levels should spike as the sun's shielding falls away, and the magnetic field should shift direction as you leave the sun's influence and enter the galaxies. None of that was a wild guess. It was built on decades of solar wind measurements and basic plasma physics, tested and retested long before either Voyager got anywhere near the edge. Voyager 1 had already crossed this boundary once before, back on August 25th, 2012, at a distance of about 121 astronomical units from the sun. But Voyager 1's dedicated plasma instrument, the one built to directly measure density, temperature, and speed, had already failed years earlier, shortly after its Saturn flyby in 1980. So when Voyager 1 crossed the heliopause, scientists were flying partially blind, forced to infer what was happening from indirect evidence and a lucky solar shockwave that happened to ring the local plasma like a bell more than a year later. Voyager 2 was different. Its plasma science instrument was still fully functional. For the first time, humanity had a spacecraft crossing this boundary with a working sensor built specifically to measure exactly what was happening to the plasma in real time. Read that again. This was the crossing scientists had actually been waiting for. What that instrument recorded, once researchers at Johns Hopkins, Caltech, and half a dozen other institutions had time to analyze it, turned out to be stranger than the tidy model anyone had drawn on a whiteboard. As Voyager 2 closed in on the boundary, inside roughly 140 million miles of it, the surrounding plasma began to slow down, compress, and heat up dramatically, exactly the kind of buildup you'd expect at the wall of a bubble under pressure from both sides. Researchers had recorded increased plasma density both before and after the crossing, a compression signature on either side of the wall that suggested something was actively squeezing the boundary from both directions at once, the outward push of the solar wind on one side, the inward resistance of the galaxy on the other, meeting in a compressed, turbulent seam. Then, on The other side of that boundary, in what was supposed to be the cold, quiet interstellar medium, the temperature came back at more than 54,000 degrees Fahrenheit, north of 30,000 degrees Kelvin. Sit with that for a second. That is roughly 5 times hotter than the surface of the sun itself. This is not a wall of fire in any literal sense. The plasma out. There is so thin, so diffuse, spread across such enormous distances that the actual heat energy involved wouldn't even singe a piece of paper. But the temperature reading itself, the raw physical number describing how fast those particles are moving, is not something the pre-2018 models comfortably accounted for. Here's where it gets worse. The magnetic field on the far side of that scorching boundary wasn't supposed to look anything like the field inside the heliosphere. Crossing into interstellar space should mean crossing into an entirely different magnetic regime, shaped by entirely different physics. Instead, Voyager 2's magnetometer found the interstellar field running almost exactly parallel to the field inside the bubble Voyager had just left. That result had already surprised scientists once when Voyager 1 found the same thing back in 2012. Now Voyager 2, crossing at a completely different point on the boundary, at a completely different phase of the sun's 11-year activity cycle, confirmed it wasn't a fluke. It is not 2 separate anomalies. It is one pattern, showing up twice that nobody's model fully explains. And then there was the leak. Voyager 2's low-energy charged particles instrument detected something that shouldn't have been possible if the heliopause were the clean, sealed boundary everyone had pictured, a steady trickle of particles from inside the solar system slipping directly through the wall into interstellar space, and in the opposite direction, streams of interstellar material bleeding back in. Scientists studying the data were direct about what this meant. If the heliosphere is a ship sailing through the galaxy, its hull is somewhat leaky. What most people are not seeing when this gets summarized is that this wasn't a one-time glitch specific to Voyager 2's location. Researchers, comparing Voyager 1's data from 2012 to Voyager 2's readings from a completely different part of the boundary in 2018, confirmed the leakiness shows up in 2 very different regions of the heliosphere at 2 very different times. It is not rare. It is not local. And as of the papers published on it, there is still no confirmed explanation for what is actually causing it. Here is where this stops being an abstract physics puzzle. That leaky, superheated wall is the only thing standing between the inner solar system and the full, unfiltered blast of galactic cosmic radiation, high-energy particles accelerated by exploding stars across the galaxy. Voyager 1's own measurements showed the heliosphere blocks more than 70% of that radiation before it ever reaches Earth. Every human being who has ever lived, every satellite in orbit, every future astronaut who leaves the protection of that bubble depends on the integrity of a boundary that 2 working spacecraft have now shown to be porous in ways nobody fully predicted. Any future mission planning to send astronauts beyond the reach of the heliosphere, a prospect still decades off, but one already being discussed in mission design papers, will have to account for a boundary that behaves less like a sealed hull and more like a slowly breathing membrane. This isn't a museum piece from 1977 doing academic busy work at the edge of the map. It is the only real-time inspection humanity has ever run on the wall protecting its own solar system. And the inspection came back with an anomaly nobody has closed the file on. But before any of that data could keep flowing home, Voyager 2 itself nearly went permanently silent. Not from age, not from cosmic radiation, but from a single misdirected command sent by its own ground team. A spacecraft this far from home has no room for error in the first place. Every command sent to Voyager 2 has to be composed with total precision because there is no way to interrupt a signal once it's launched toward the antenna, and no way to know it went wrong until a response, or the absence of one, arrives most of a day later. On July 21st, 2023, engineers at NASA's Jet Propulsion Laboratory sent what was supposed to be a routine sequence of instructions to the spacecraft. Buried inside that sequence was an error, and the result tilted Voyager 2's high-gain antenna just 2 degrees off its lock on Earth. 2 degrees. Think about what that means. At a distance of more than 12.3 billion miles, a misalignment smaller than the width of your thumb held at arm's length was enough to sever every line of communication humanity had with the most distant working spacecraft it had ever built. The moment that antenna drifted off target, Voyager 2 could no longer hear commands from Earth, and Earth could no longer hear anything meaningful back. It just went quiet. For engineers at JPL, this was close to the worst-case scenario the mission had ever faced. There is no backup spacecraft. There is no repair crew that can be dispatched. The probe's own onboard fault protection system did have a safeguard built in, a scheduled realignment maneuver program to automatically reorient the antenna back toward Earth. But that safeguard wasn't due to trigger until October 15th, nearly 3 months away. 3 months of total silence from a 46-year-old machine that had already survived nearly 5 decades of cosmic radiation, extreme cold, and mechanical wear-no engineer in 1977, designed it to endure. The team wasn't willing to simply wait and hope. On August 1st, using a routine sky scan, the Deep Space Network picked up something. A faint carrier signal, a heartbeat, proof that Voyager 2 was still alive and functioning, even though it couldn't hear a word being said to it. That was the confirmation the team needed to try something drastic. On August 2nd, engineers at the Deep Space Network's Canberra facility in Australia aimed their most powerful transmitter directly at where Voyager 2 should have been, and fired a 100 kilowatt signal into the dark, what the team itself would later describe as an interstellar shout, a command sent with far more raw power than a standard uplink, in the hope that it might be strong enough to reach a spacecraft whose antenna wasn't even pointed at Earth anymore. Then came the wait. At that distance, a one-way signal takes about 18 and a half hours to arrive. Round trip, confirmation either way was going to take roughly 37 hours. The better part of 2 full days spent not knowing whether humanity's connection to its most distant machine was about to be restored or lost for good. On August 4th, at 12:29 in the morning Eastern Time, data started streaming in again. The shout had worked. Voyager 2's antenna had swung back into alignment, and the spacecraft resumed transmitting normally, its trajectory undisturbed, its instruments intact, as if the entire 2-week ordeal had left no mark on the machine itself, only on the people back on Earth who had spent those weeks wondering if they'd just lost it. It remains to this day the longest single silence in the entire history of the Voyager mission, and the closest either spacecraft has come to vanishing, not from age or distance, but from a single line of code sent by the very people trying to keep it alive. Here is what is happening right now, in 2026. Voyager 2 is roughly 13 billion miles from Earth, about 21 billion kilometers, or 142 times the distance between the Earth and the Sun. And every command sent to it now takes close to 39 hours to get an answer, there and back. Its 3 remaining functioning nuclear generators are still converting the heat of decaying plutonium into electricity, but they lose about 4 watts of available power every single year, a slow bleed with no way to reverse it. Of the 10 original science instruments, Voyager 2 launched with, 7 have already been permanently switched off, some because they were only needed for the planetary flybys decades ago, most in recent years purely to conserve dwindling power. The plasma science instrument, a different sensor from the plasma wave subsystem that caught the leaky boundary signal, was itself switched off in September 2024, its usefulness limited once the spacecraft moved beyond the reach of the solar wind it was designed to sample. As of this year, 3 instruments remain alive: the magnetometer, the plasma wave subsystem, and the cosmic ray subsystem, the very fields and particles instruments most capable of continuing to probe exactly the kind of boundary anomaly this story has been building toward. That cosmic ray subsystem was actually scheduled for permanent shutdown before the end of 2026. Losing it would have meant losing one of the last 3 windows humanity has left onto a region of space no other instrument will reach again for decades, since no funded successor mission to interstellar space currently exists on any space agency's books. In early August of this year, engineers at JPL completed a delicate, high-stakes maneuver they've nicknamed the Big Bang, simultaneously swapping several power-hungry components for lower-power alternatives, all at once, rather than gradually, while keeping the spacecraft systems warm enough to survive the swap without freezing its fuel lines in the process. It worked. The power freed up by that single coordinated procedure is expected to keep all 3 of Voyager 2's remaining instruments alive for at least 1 additional year, buying humanity's only working interstellar sensor network more time to keep listening at the edge of the wall it discovered in 2018. The same procedure is now being prepared for Voyager 1, which faces its own version of the same countdown roughly 2.5 billion miles farther out. And there is a date already locked into that timeline, one that requires no prediction at all, just arithmetic. On August 20th, 2027, Voyager 2 will mark 50 years since it left Cape Canaveral. 50 years of continuous operation from a machine engineered with 1970s technology, designed for a mission a tenth as long as the one it has actually flown. Every command sent to it by then will still take close to a day and a half to complete its round trip. And by then, its power output will have fallen further still, 4 watts, shaved. Away every year, with no way to add a single watt back. Mission scientists who have spent their careers on this program have said plainly that they expect the spacecraft to still be in contact with Earth when that anniversary arrives, its radio still faintly reaching across more than 13 billion miles of empty space, still reporting from the edge of the same superheated, leaking boundary it punched through in 2018. Beyond that, the mission team's own stated goal is to keep at least 1 instrument alive on each spacecraft into the early 2030s. Not as a guarantee, but as the interstellar material seeping in is still not fully explained. Researchers studying the Voyager 2 data have pointed to a couple of competing possibilities. It could be a form of magnetic reconnection, where the sun's magnetic field lines and the interstellar field lines briefly link up and swap material across the boundary. similar to processes seen much closer to home in Earth's own magnetosphere. Or it could be a more general turbulent mixing at the edge of the bubble, driven by the same pressure imbalances that compress and heat the plasma there in the first place. Neither explanation has been ruled out, and neither has been confirmed as the dominant mechanism. The data from a single flyby, gathered by a spacecraft moving in one direction along one narrow path through the boundary, simply isn't enough on its own to distinguish between them with certainty. Scientists involved in the analysis have been candid that they don't yet fully understand what is causing the compression and leakage on either side of the wall. That is not spin, and it is not a cliffhanger manufactured for a video script. It is the honest state of a measurement made at a location no other instrument has ever occupied, using data still being picked apart by researchers who, in some cases, are analyzing readings the original mission architects never lived to see. Zoom out from the specific numbers for a moment, and there's a bigger pattern sitting underneath this entire story. 2 machines, built with slide rule era engineering, sent out with a 4-year mission plan and a prayer, ended up performing the only direct physical inspection humanity has ever conducted on the boundary that shields our entire solar system from the rest of the galaxy. And what they found didn't match the tidy diagram. It was hotter than expected. It leaked in ways nobody predicted. It kept surprising the very scientists who built the models it was supposed to confirm. That is not a failure of those models. It is what happens every time a genuinely new instrument reaches a genuinely new place. The universe turns out to have more texture than any diagram drawn from a safe distance can capture. What most people are not seeing is that this has been the actual pattern of nearly every major leap in space science. Not a triumphant confirmation of what we already suspected, but an uncomfortable correction delivered by hardware that outlived the assumptions of the people who built it. Voyager 2 wasn't sent out to discover a leaky, superheated wall at the edge of the solar system. It was sent to fly past 4 planets and come home with pretty pictures. The wall found it on the way out, and it's still transmitting details about that wall today, more than 49 years after launch, from a distance so vast that the very act of asking it a question now takes almost 2 full days to answer. Consider, too, what it means that the people currently making sense of this data were not the people who designed the instruments collecting it. The plasma wave subsystem now confirming a persistent anomaly at the heliopause was built by engineers in the 1970s who had no way of knowing what it would eventually find, decades after most of them had retired. That's not incidental to how this kind of science works. It is the actual mechanism. A single well-built instrument, kept alive far longer than anyone intended, can outlast the entire scientific generation that launched it, and still keep handing new questions to the next one. There's a small, dark object drifting through that furnace-hot boundary right now, still carrying a gold-plated record bolted to its side. Greetings recorded in 55 human languages, whale songs, a Bach's fugue, the sound of a mother's first words to her. Newborn child, all etched into copper and sealed against a universe that has no obligation to ever find it. It crossed the hottest wall humanity has ever measured directly, and it did not slow down, and it did not stop transmitting, and it carries that record outward still into a darkness so complete that the sun itself is now just one more indistinguishable point of light among billions, receding a little further every single day, forever, whether or not anyone is left on the other end to listen. Somewhere in the mission's own archives sits the plaque affixed to that record's cover, etched with instructions for a civilization that has never heard of a phonograph, a map pointing back toward a small yellow star that, by the time anyone finds it, may no longer even resemble the sun humanity once knew. So here's the whole arc, in one breath. Voyager 2, launched in 1977, became the only spacecraft to fly past all 4 outer planets, and crossed into interstellar space on November 5th, 2018, where its still-functioning plasma instrument recorded a boundary hotter than 54,000 degrees Fahrenheit, and a magnetic field that shouldn't have lined up the way it did, but matched what Voyager 1 found 6 years earlier. Scientists confirmed the heliopause leaks material in both directions, in 2 separate locations, with no fully agreed-upon cause. In 2023, a single misdirected command nearly ended the mission for good, until a 100-kilowatt shout across 12.3 billion miles brought the antenna back into alignment. Today, in 2026, 3 instruments remain alive. Power keeps dropping 4 watts a year, and a fresh power. Saving Maneuver has bought at least 1 more year of data from the edge of that unexplained wall, with the spacecraft's 50th launch anniversary now locked in for August 20th, 2027. If a story like this is the kind of thing you want more of, subscribe and turn on notifications, because there's more coming on what Voyager 1 and 2 find next as their power runs down through the rest of this decade. Here's my question for you. If you had to choose, would you rather NASA spend the next few years fighting to keep these 2 50-year-old machines transmitting, Or let them go quiet and pour everything into a new interstellar probe built with the technology we actually have today? Tell me which one in the comments. I read every single one.